In this lesson, we're going to be finding the area between two curves. We'll be reviewing how we calculated area back in Chapter 4 when we talked about the application of an antiderivative being the area under the curve bounded by the x-axis. We'll practice finding area between two different curves, both in terms of x and in terms of y. So back when we started using integrating and we were trying to estimate the area under the curve, we estimated the area under the curve by doing the area of a rectangle. So if you recall, the definition of a definite integral is the sum of an infinite number of rectangles, where the height of the rectangle comes from the function at that point, and the width of the rectangle is delta x or dx. So back in Chapter 4, when we practiced with this concept of finding area under a curve, we did something like this problem. Sketch and find the area under the curve bounded by the x-axis and the lines x equals 2 and x equals -1. So one of the first things you probably did if you weren't provided with one was to sketch out the region that you were finding. So if f of x is x squared plus 2, so the parent graph shifted up 2. So get in our sketch of the parabola there. Okay, and then from when x is -1 to x is 2, so I'll just shade in that region there. Alright, so if we want to find the area of that region, we just go ahead and we set up the definite integral. So lower bound -1, upper bound 2, x squared plus 2 quantity dx. Okay, so there's the height of our rectangles, there's the width of our rectangles. So if we go ahead and take the antiderivative of that, so 1/3 x cubed plus 2x from -1 to 2, we go ahead and plug in our upper bound for x for all those values. So 2 cubed is 8, so I have 8/3 plus 4 minus, then I plug in -1, -1 cubed is -1, so -1/3 minus 2. And if we go ahead and just finish the arithmetic on that one, I end up getting an area of 9. So that was how we applied the idea of a definite integral back in Chapter 4. So we're just going to expand what we're looking for today a little bit. So for example, we'll look at a situation where our area is not bounded by the x or y axis. So let's go ahead and look at the same function, the f of x equals x squared plus 2, but let's let our lower bound be the line y equals x minus 2 rather than the x-axis, and we'll continue with the same boundaries of -1 and 2. So let's come up with the sketch. So again, we have the parabola shifted up 2, so 1 away from the vertex you're up 1, 2 away you're up 4, 1, 2, 3, 4. Okay, and then our lower bound is the line x minus 2, so y-intercept of -2. Okay, and then from -1 to 2. Yep. And then going to color that just a little bit different just so we can explain where this area comes from. So if we want to go ahead and find the pink area, so the area under the parabola bounded by the x-axis here, we just calculated that. So from -1 to 2 of f of x dx, we had just calculated that area to be 9. Well, the area from -1 to 2 of x minus 2 dx, if we go ahead and calculate that, you can either use the area of a triangle formula if you're interested in that, or you can actually take the antiderivative, but that area turns out to be -4.5. So if we want to find the area from under the parabola all the way down to that line, if we want to find that total area, it would be 9 plus 4.5, which would be 13.5. All right. So let's just look at another type of area that we might be working on today. So what if we were calculating this area for an equation that was written in terms of y instead of x? So if we want to find the area bounded by the curve y equals 0 and y equals 1, and that curve is x equals 3 minus y squared. So this is a parabola turned on its side, shifted right 3 and flipped going this direction here. So if we want to find the area from 0 to 1, this is the region that we're referring to right here. And so when we're calculating the area, it would be like our rectangles are going this way. So this time the height is still coming from the equation, and the width of these rectangles then is going to be dy. So when we find this area, the bounds are going to be y bounds. So from 0 to 1, the heights are coming from the curve written in terms of y, and then the width of each of those rectangles is dy. So so this area turns out to be 2 2/3 when you end up going through everything. Okay. All right, so let's just go ahead and do another one. So let's find the area bounded by the curves y equals 2 minus x squared and y equals x. Okay, so we're shifted up 2, opening down. So this time they didn't end up giving us any boundaries, they just gave us these two equations as our boundaries. All right, so if they want us to find the region where these intersect, that would be the yellow region that we have right here. And we need to know x boundaries or y boundaries, so we would want to know where these intersect. This is intersecting at the point -2, -2. This is intersecting at the point 1, 1. So I'm going to be going from -2 to 1. And to get all the way from here to here, that length is, so from the parabola down to the axis, that's 2 minus x squared, and from the axis down to the line y equals x would just be x, so it's going to be 2 minus x squared minus x would give you this length right here, which is top curve minus bottom curve. When everything's said and done, we do get the area of this here to be 4.5. Okay, so in general, just to summarize, when we're finding the area between two curves, if we're integrating in terms of x, we take the top curve and subtract the bottom curve. If we're integrating in terms of y, we want to take right curve minus left curve. So if we find the area bounded by the curves, f of x equals x minus 1 quantity cubed, and g of x equals x minus 1. So the cubic here is graphed in blue, and the line is in red. So if we want to find that area, it's like that. You may need to use your calculator to find the intersection. The intersections here are 0, -1. They won't necessarily always be whole numbers. 1, 0, and then 2, 1. All right, so we had just mentioned that if you're going to do this with dx, that you'll want to do top curve minus bottom curve. Well, when we get into this region over here, the top curve is the line, the bottom curve is the cubic, but over here the top curve is the cubic and the bottom curve is the line. So if the top or bottom curve ever change anywhere in your region, you'll need to write multiple integrals to be able to calculate the area. So when we're doing this one, if we just want to set up what the integral would look like, so I'm going to integrate from 0 to 1, so I'll take care of this region here first. The top curve is the cubic, which is f of x, so I'd have to do f of x minus g of x in that region. And then in the other region, it's the line that's the top curve, and I'm going to be integrating from 1 to 2, so that'll be g of x minus f of x dx. So that would be how I would calculate the area of this whole region. So it's not uncommon for you have to write more than one integral to find the area of a shaded region between two curves. Under the curve bounded by y equals x to the 1/2, which is y equals the square root of x, the line y equals x minus 2, and the x-axis. So we want to find the region bounded by all three of those. So if we shade in that region, here's what we're referring to. It's not uncommon to be bounded by more than two boundaries, so you might end up having a situation like this. So again, let's go do a quick check to see if the top and bottom curve change at any point throughout this, because then that'll involve a split for finding the area. So in this region, you can see that from the top to the bottom, top curve square root of x, bottom curve's the x-axis. Same here, but then when we get to right here, there's a split. The top curve is going to be the square root of x, the bottom curve is going to be a line. So I'm going to call this region 1 and this region 2, and I'm going to need two different integrals to be able to calculate the area of the total region. So if I want to find the area in region 1, I probably want to know what the boundaries are. This is when x is 2, and over here, this is the point 4, 2. So when I'm finding the area of region 1, I'm starting with a lower x boundary of 0 going up to 2. The square root of x being the upper bound, the bottom curve being 0, so I don't need to write minus 0, so just square root of x dx. Then at region 2 starts at 2 and ends at an x upper bound of 4. It's going to be the square root of x minus 2 dx. Alright, so then if I go ahead and integrate this, I end up getting a total area of 3.333. So if you're curious, as a reminder, you can do some of this by hand, so this is something that you could easily do by hand, but if you had wanted to use your graphing calculator to help you with that, notice that I have square root of x in my y1 and x minus 2 in my y2. So if I want to integrate that from my home screen, you can go Math, Function Integration number 9. So from 0 to 2, and you can either type in the equation, so like square root of x dx, or again, if you had wanted to use your y1 and your y2, you can do that also. Just kind of want to review these couple techniques so they're fresh in your mind. And those are typed in terms of x, so it is going to be dx just like on the last one. Okay, so that would be a different way to evaluate besides doing it by hand. Alright, so, but if you had wanted to calculate this area a different way, only using one integral, sometimes doing things in terms of y is an interesting way to maybe simplify the situation. So what I mean by that is we had discussed how if you were finding the area between two curves and you wanted to do it in terms of y, you'd do right curve minus left curve. Notice that in this region, when you go from right curve to left curve, the right curve is always the line, and the left curve is always the radical function. So we could find this area only using one integral if we had done this all in terms of y. So if you don't have the equations in terms of y, what you would have to do first is to solve for the other variable. So if I have y equals x minus 2, if I add the 2 to the other side, I get x equals y plus 2. If I want to solve for x equals on this one, if I have y equals the square root of x, if I square both sides, I get x equals y squared. So in the lower boundary here, this is when y is 0, and this is up to when y is 2, and my right curve being the line, so y plus 2 minus the left curve, which is y squared dy. So then I can do this all as one integral. Okay, since I'm finding the same area of the same region, I would expect to get the same area. So when you integrate this, we'll just review doing it on our home screen again, you'd want to just put this in terms of x. That would be, so we'll put in 2, and then we'll put it in as x plus 2 minus x squared. Notice I'm not using my y1 and my y2 because those are different functions. Oops. Okay, so we end up getting the same area. Alright, so in this lesson we just reviewed how you can find the area between a curve and the x-axis using a definite integral, and then we showed how we would modify that to find the area of the region bounded by two or more curves. Sometimes if the top or bottom curve change as you're working, you may need to split the area up into two or more integrals, and then sometimes if you want to represent the area both either dx or dy, the number of integrals or the way that you need to write those will be different. So those will be the skills that you're practicing in this lesson.